Hi, it's great to have you here. Today we are looking at another DSA question called word search. Let's get started and break this problem down in a way that makes sense. The problem statement says that we are given an m into n grid of characters board and a string word. We have to return true if the word exists in the grid. The word can be constructed from letters of sequentially adjacent cells. So what this means is that if you're given a matrix and you're on an element, you can either go up, right, bottom, which is down, or left. Another condition given is that the same letter may not be used more than once. Let's look at this with an example. So let's say you're given this grid, which is the board, and the following string that we have to look for. So if you look closely, the following string can be created if you start from this character, which is A, you go right, becomes B, C, C, E, and D. So this path in green here, this is a string that we were looking for. Further, let's observe that when we created this string in our grid, we only went sequentially on the adjacent cells, which means we either went to the right or we went down or we went to the left. We did not go diagonal. And in addition to that, we only used one letter cell at once. We did not use it more than once. Let's break this problem down with the help of RACE framework. So the RACE framework stands for Reason, Approach, Code, and Evaluate. We have a video for this on our channel. I'll link it down below. Definitely look for it. Let's start with reasoning with the question. Let's start with looking at our example more closely. So here is the example that was given to us. So given this example, if we start with the first character, either we can go to the right because we can only go to sequentially adjacent elements, or we can go bottom to the left or up. Let's draw and understand this better. So given A, which is our starting point, either I can go down, which is S, or I can go to the right, which is B, or we can go up. In this case, it is nothing because we don't have anything on the top. So, and then, or we can go left. We do the same from S. Either I can go down, right, up, or left. So from S, if I go down, I see another A. If I go right, F is to the right of S. If I go up, I see A, and to the left, we have nothing. Now please notice here, when we go up from A, this is the A that we came from. So this is the same A. So this A is the A that we have already seen in the past. So we cannot go back here. And this is exactly why this backtracking problem is different from the others. Here, we'll have to keep a check of the elements that we have visited. So if we started from A and we went down to S, we cannot go back to A. So this is something we cannot do because it is given in the question that we can use each character in a cell at most once. Another observation that we can make here is that this will be traversed in a depth first fashion. So once you go from A to S, we'll keep going to the left until we hit the terminal condition. Let's write both those observations down. So the first one was we have to keep a track of visited. And the second observation that we made is that this will be traversing depth first search. With that, let's look at the third and the final observation, that once you see S after A and you know that we are looking for A, B, C, C, E, D, you know that we're looking for B and not S. So this becomes a terminal condition. So we'll not further traverse out from S because S does not exist in our string that we're looking for. Let's make another observation, the third observation. We were looking for A, B, C, C, E, D. So the third observation will come from, so when you're moving from A to S, and S does not happen to be the character that we're looking for. So here we are looking for B. So if S does not happen to be the character that we're looking for, we will not further branch out from S. So we'll not branch out from S and we'll backtrack from here itself. We'll just go and see if we can find B or not. So that becomes our third observation. Let's quickly write that down. Let's move on and dive into the approach section. If we look at our example once more and see that this is where the answer is, let's try to create the tree from this and we'll try to understand how the approach will go from there. So let's say we start from A, and the 4 options from A, like we did, it's down, which is S, and then B, and these are our, there's nothing there, so we'll just end there. S is also not a match, so we'll not proceed from here. Further, when we come on B, we'll make similar calls. So we'll go down first, which is F, and then C, and then the other 2 calls are again terminal calls because we don't have anything there. F is not in our solution set, so our solution string is A, B, C, C, E, D. Of these, we have already found A and B. Next, we are looking for C. So F becomes a terminal case here. We continue from C. From C again, we can go down, which is C, and then E, which is on the right, and then we have 2 more dead calls, up and right? So again here, E becomes a terminal case, and we keep going, and from this C, either we can go down, which is E, S, top is C, which is already seen, so we'll not go there, and then we have F. So F again becomes a terminal case here. Okay, and after E, we have, again we go down, which is again a terminal case. We go to the right, and we are not looking for that. E, look for S. So from E, again we go down, which is no up. We go to the right, which is an E. We go to the top, which is C, and then we go to the left, which is D. Again, this E and C are again their terminal cases because this C is in our visited, and E is not what we are looking for, and D is what our final state will be. So if you track this path, A, B, C, C, E, D, we found our answer. So if we just check that path again, we got A, B, and this is our C, another C, E, and D. So we got our solution, and this will be our final answer. So the approach for the code is pretty clear here. What we'll do, we'll have to start from each element. So it'll be a loop where we start from each element, and then we'll make 4 recursive calls. One to the down, where we have one possibility, one to the right, one up, and one to the left. So we'll make 4 recursive calls, and while we do that, we keep track of our visited. So visited is something new that we are seeing here, and this is because a lot of the backtracking problems there, like combinations and permutations, they are sort of unidirectional, because when you explore the possibilities here, they work as a tree. That means there are no loops. But in this case, this is actually a graph where you will see loops, and if you don't keep a check for visited, you'll get stuck in them, and that will not work. Let's go and see how the code for this will look like. Okay, let's look into the code. Let's start with creating 2 variables, one for the number of rows, and that will be number of the length of the board, so which is essentially the number of rows, and one will be for a number of columns, so this will be capital C, and that will be the length of that, right? And then let's iterate over our matrix one element a time. So this will be a 2-degree loop. The outer loop will go over the number of rows, so self.r, right? And we'll range over this. Similarly, for the columns also, we'll range over C, capital C. And here, let's create our backtrack function, which will essentially be our recursive function. So we'll pass the entire board here, and then inj for our current position on the board. Current variable will carry our intermediary result for each node. And then we have our target string. Visited is a set. We'll create a set to track our visited. And then we'll have a pointer. Pointer will be the pointer on the answer string. So let's call it our target pointer. So TGT pointer, which is our target pointer. All right. So this is what our function will look like. Next, let's just write this down here. So that's what we'll call. for each of our cells, and if any of the cells return the answer back to us, that's where we'll exit. So we'll just say if res, which is if res is true, if the result is true, we just return. So we just return, right? And if we don't get an answer from here, we return false. This completes our basic structure. Obviously, we'll need to write our backtrack, which is the crux implementation. Let's get on with that. Before carrying on to write with the backtrack, let's make sure that we have completed our call here. So let's call RNC. So we'll start from each cell. That's what RNC is. Current will be an empty list. So we'll keep appending to our list here, whatever the answer, whatever intermediary characters that we get while we do recursion. This will be our set, which we'll need for tracking visited. Target will be target. So let's just call that word because that's what is given. And we'll start with a 0 each time when we start with a position in the cell. So that's what becomes our initial call. R and RNC, and then current set for tracking our visited. Target is word, and then the target pointer is where we start our recursion for each cell from for the answer word. Okay, let's now look at completing our backtrack. So like we talked, we'll make 4 calls here. One down, the other call will be to the right, so we are going counterclockwise. Then we go up, and then we go left. So the call will look something like this. So when we go left, down on the board, down means that we'll increase the row. Current will add the current element, so that's very straightforward. I and j. Visited is whatever visited, so we'll add the current element in visited in just a second. Target will remain target, and pointer will just increment itself because we want to see the next element in the next call. So carrying on, let's quickly complete our right call. So the right call will be, it's the same row, and we increment our column. The pointer will be the same, ij remains the same, so everything else remains the same. Up will be where the column remains the same because we're going up the column, but our row will decrease, right? And then left will be where j is -1, which is our column -1, and everything else remains the same. So this becomes the 4 calls that we're going to make. Now you'll naturally wonder, right? Like the very first thing we'll have to check is what if our I and j run out of bounds? So for that, we'll first put a terminal condition. So if I is greater than or equal to our number of rows, which is self.r, or I is less than 0, that is also out of bounds, or j is greater than or equal to our self.c, or j is less than 0. So if any of those conditions satisfy, we just return false, right? Another terminal condition that we'll have to make sure is that if, let's say, once the boundary conditions are met, we'll have to make sure that if I see my current element, so if cur equals to my target, so if I have found the solution, I just return true, right? So that's my success case. Let's call this our boundary terminal, right? And then one final thing that we'll need is that if the condition, the position that we're trying to visit, so if I and j, which is a tuple, so this is a tuple data structure, this is hashable, so if this is visited, that is also when we just return false. This is because we want to avoid any loops. That's that. And once all these conditions are satisfied, what we do is we just do this. So once all these are satisfied, we are sure that we want to visit the current element. So we'll just say visited.add, and we'll say I and j. So this is the tuple that we add. And another very important case here, which we missed. So we want to make sure that the current element that we're seeing after all these conditions are met, it is one of our solution. It is in our solution character. So how we do that is we just compare if the target that we're looking at. So if the current PTR that we're looking at. So if this if this does not match our current position on the board, so if this does not match, we return false. So this will make sure that all the branches where our character does not match, we don't really go and start traversing those branches, and our tree and our iterations get saved. So that's it. That's what our code will look like. If I zoom that out for you, let's quickly look at that. So if I zoom that out for you, let me just remove this. So this is what our code will look like completely. There's one thing missing here. We have not taken care of the cases. One when the call will return of any of the cases, so we'll have to handle that. So let's say this was our up, so we'll just collect these in a variable, and this was our down, right, and this was. So if we get answer for any of this, we have to return up, down, or right, or up, or left. So this is what that is. One of the things that we are missing here. Now, if you look closely, this is where backtracking really starts to show itself. So when we are backtracking, we have to make sure that we mark that position as non-visited, so that, you know, if it comes back, it is able to use that element. So we have to remove it when we are done checking all our calls. And that's it, folks. I think this code is now complete. Let's try to run this on our test case that we given. Oh, it says backtrack not defined. Let's quickly see if we, oh, okay. Okay, I think I've fixed that now. Let's try to run that once again. And we got another error. Let's see. Oh, I see. Here we are trying to attach add a character to a list. How about we just, the problem was that we are trying to attach a character to a list, which doesn't work. So that's that. Let's try once again. Okay, looks like that worked. All our test cases pass. Let's try to submit that and make sure that it is accepted. Looks like we did not consider another use case where the board can have just one element. For that, either you can add a check here, but I think a cleaner approach would be that we put this condition as first. So we just check this condition as the first condition. So we'll run that once again, and we can also submit this now. Okay, so that got accepted, which is pretty good. If I would go back and think about this code a bit more, I would focus on these two lines. And then this is also a very important condition. If you remember, this was down here. We moved it up so that it can address one of our use case where if the block has just one character. So this is pretty good. I think if you do that in the interview, the interviewer will definitely appreciate this, that you were able to identify and use the existing algorithm rather than add a new check. So that's always appreciated. And yeah, and then you have to start from each element. Again, if you find the answer, you return it. So if you get a result, you just return it. You don't have to further go and check other elements there. And that's it. Let's move back to our writing pad and look at the evaluate now. Let's proceed and just mark our code section done. Let's look at the evaluate section now. So the time complexity in big O notation will be number of rows into number of columns into 4 to the power L. So here L is the length of our target word. If you start thinking about this R and C, that's pretty clear because we are doing a recursive call from each element in the matrix. So if there are number of rows in the matrix is R, columns is C, it will be R into C. And then for each of those elements, we are doing a recursive call where each element does 4 calls, and the depth of the tree is directly is L. So it goes as deep until we find our answer. So that's why the time complexity, the third part of the time complexity, becomes 4 to the power L. If we now think about the space complexity, that'll be big O L. It's L because you have the call stack in your memory. And the utmost length of the call stack will be equal to the length of your target word, which is L. So if you see, this is a recursive DFS approach. At max, you will have the call stack equal to the length of the word. And that's pretty much it. Thank you so much for following along, and see you in the next one.